Good afternoon, and thank you very much for inviting me for this conference. So my talk is more or less a advertisement of my web servers because that's a part of the business. Because we are the developers, software developers. So there is no use to develop the software if no user is there. So for us, most important part is advertisement. Though in scientific term it is not considered good practice to advertise your work, but from computer point of view, we need the user. Though all softwares, all services, they are freely available to the public. We have no restrictions at all. So over the years, I entered in the field in different fields. So it's not one field. Initially, I worked to develop the small softwares for my institute. Then I realized that there are only limited users in my institute. Then I make it open, publish it, advertise it more, so that more and more people can use it. So these are the small softwares, how to do the restriction gene mapping, how to do the antibody antigen concentration, simple stuff. But I become bored again in small softwares, then I go to the vaccine development. Vaccine development or immunologics excite me most. Why? Because it's an interesting story. What is going on? What type of fight is going on inside your body? That how the virus, bacteria, fungus is attacking you, and same time how your immune system is defending. So it's a good fight between two. Okay, whoever will take the lead. Okay. Then genomics, proteomics come in between. So we jump into the genomics, proteomics. Then still I realized that I am still working on the bioinformatics part. But what you will do with the drug targets? Because in the bioinformatics, we mainly focus on the drug targets or some annotating some protein or annotating some biomolecules, basically. So even if you know the drug target, what you will do? So we jump into the area of drug discovery, in silico drug discovery, where we develop the QSAR models and other business. Then I realized too many people are there in the drug discovery. It's difficult to survive there. We jump into the peptide and protein-based therapeutics. Means rather than using the small chemical as a drug molecule, we can use the peptide and proteins, that's a biological molecules that are found in the nature. Okay, as a therapeutics. Then we use. After working too many years, question was what type of tools are available. So too many people are working worldwide to develop the different type of tools. So what we did, we compiled lot of resources available from literature. The condition is that it should be related to the healthcare because healthcare is a big umbrella. If I say drug discovery, then it's a small umbrella. Okay, and try to compile it, but still it's not possible to compile all resources in a one review. So we put our website because the one purpose I had from beginning that how to help the community. I'm not a great scientist, I'm not a deep thinker at all actually, but the intention is very clear, how to help the community. Okay. So this is a small work, but useful. Means where we have compiled all the resources, all resources in databases, mobile apps, or web servers, standalone softwares at a one place so that you can go there and then you can find out the link related. This is my website. From where you can get all these resources. The challenge was that when I read the literature, you find a review on chemoinformatics, bioinformatics, pharmacoinformatics. These are the different type of informatics. Though they are overlap to each other, they are doing the similar type of work. Okay. So then I thought that why we should not combine a single. So I put in the term the softwares related to the healthcare because it's a big umbrella. It's considered the vaccine, biomarkers, drug discovery, all sorts. Then next question was, once you compile everything, then you have to group it again so that people can understand better. So we group it in the term of the drug discovery topic. In drug discovery, again, it may be chemical based, small molecule based, it may be peptide and protein based. So we cannot go for the more, let's say, carbohydrate and other things. So we focus only two type of molecules, small molecules and peptide and proteins. Then next major challenge was how to predict the toxicity, side effects of these drugs. Because that's a major challenge nowadays. Third is healthcare, vaccine development. So in vaccine development, because that's my favorite field over the years, at least that's the only field where our group is working last more than 20 years actually. In other fields, we left the field. Though vaccine informatics we left in between, and then we feel it's required, and then we again jump in. Still we are working. So that's a favorite field. Next is disease biomarkers. That's another important area because you want to know, let's say, whether the cancer is there or not. If cancer is there, in which stage is the cancer is there, or what is the risk. So that's a cancer example. For other disease also, we have to have the biomarkers. Then next is basically more towards the IT people actually. That's called healthcare and IoT. IoT things, you know, Internet of the Things. That where you have the mobile app, telemedicine, sensor based. So this is nothing. It's a simply compilation of different tools in one. Just to give you the idea, particularly the researchers here in this audience is more towards the computer science. So they should have some idea what type of problems they may consider to develop. Because ultimately you have to develop. So this is a just example because there is a misconception in the public. Because most of the people feel that drug means small molecule based drugs. Drug means small molecule based drugs. But that's not true. There are a number of peptide and protein based drugs have been already approved by FDA. So first thing what we did actually a few years back, we created a database of therapeutic peptide and proteins. All these peptide and proteins have been approved by FDA. Okay. So we provide the comprehensive information just to give the idea that what type of information is available. I will tell you one thing. Sometimes we are too smart. We don't want to do the donkey type of work. But the donkey type of work is very important. I will tell you why I am saying this statement. If you see carefully, how many databases have been developed by Indians, that's a question. We are very smart. If you see to the PDB and other databases, if you see the statistics, Indians are the heavy users of these databases. They're heavy users. Even to go to the Google and other things, Indians are heavily using. Because we are smart people, we need the data set which is already created by somebody else. I realized this problem in the beginning. And what we decided in our group, that if you want to go into any field, we will create the databases first. Because when you are creating the database, so that you are compiling all the information of that field, so you have the depth knowledge of it. Though it's a dirty work, but in the long term, too many users are there, too many people will use it for creating the data sets. Because in computer part, without data set, no meaning. Let's say when you want to apply the artificial intelligence or machine learning or classification, what you need? You need the clean or validated data sets. Validated data set means experimentally validated data. Okay. So this is the one part of the business that takes the one database. This is not the one database. We have many databases. This is a grouping that where the peptide and protein can be used. And I will request the organizers, please share my slides to the participant later on, so they don't need to worry about the links actually. This is an example. Looks like the peptide and protein work has not been done, but if you see carefully, I have only compiled few of them actually. How to predict the antimicropeptide, blood-brain barrier peptide database, blood-brain barrier peptide predictions. Like whatever you do for the small chemicals, same thing. People are working for the peptides and proteins. And there are too many tools are already there. So if you are a computer scientist and looking for the different fields and the drug discovery, and you are interested in peptide and proteins, then you will get some of the tools here, and you can think about the better tools actually. Always there is a scope to improve. These are the examples. Too many tools are already there, and in this area we have too many tools because we are working from last 8 to 10 years in this area. After this, the next part is small molecule chemicals based drug discovery. Of course, this is a traditional field. Here, one thing I would like to make the statement. I only cover the freewares or open source software. From beginning, from last number of years, we are working and we are promoting the open source software, because one side that our researchers complain that we do not get the grant from the India, we are not able to grant grant, and also on the other side, we are wasting lot of money on the commercial software. You can save lot of money not to buy the commercial software. So please learn, when you are doing the researchers have one problem. They need the money and they spend it anything else. And they feel pride to get the big grants. They say, I got the 10 crore rupees from the DST, I get the. Well, that's not important. That's an input. You have to think about the optimization of output. That minimum grant and maximum output. If you want to follow that, you have to focus on the free softwares. Why free softwares? Because they are equally powerful as any commercial software, or sometimes better than that. So, in all my over the years, I'm promoting the open source or freeware. This is more important for developing countries like India, where getting the grants is challenging. So all these are freely available tools. So there is a drug resistance and other part of the problem. I'm not going about that actually. So we have to think about the other part, alternate tools, and particularly toxicity prediction. There is a different type of toxicity that is including the allergenicity, means allergy. They may get the allergy. That's a software for allergy prediction for small molecules. So for predicting the allergy of the peptide and protein, we developed a long time back in 2000. So this is here actually. He developed the tool. I'm jumping particularly because I have to show one case study that in today's time, how we have to develop the research. Okay. Because you can read about them, but toxicity, we have to understand there are different type of toxicity. We have covered only few type of toxicity. It may be hemotoxicity, means it may lyse the RBC. It may be cytotoxicity, simple cells. It may lyse it. It may be allergenicity. It may be other type of toxicity. So there are different type of toxicity are there. There is a lot of scope is there for the researchers. So this is an example of allergenicity. This is a recent method we have developed it. First method we developed in 2006 by Sudipto my PhD student. So we developed at that time, and this is too much in demand. We developed the new version. That's another part of the problem, because a lot of requests I got from the users that most of your tools are too old actually, and in meantime data has increased, because the performance of your model heavily depends on the size of the data. If you use on the bigger data, the chances of reliability is much higher than using the small data set. So we update them whenever we feel that it becomes too old or new data is sufficient, new data is available. So these are just examples of some of the tools which are related to the prediction of toxicity. As I told you in the beginning also, it's not possible to cover here in all tables. If you go to our website, we have covered most of the tools. As I told you in the beginning that most favorite field for us is vaccine development, because I love the area called immunoinformatics, where what we did actually different than most of the other people in the research. That we try to understand the whole story of immune system rather than working whatever the others are doing. Let's say most of the people at that time are working on the prediction of MSC binders or HLA binders. They are not considering the whole pathway, that why only MSC binder. So we go into each and every bit of the pathway. So what is a challenge actually? What is a change in the vaccines? If you go to the traditional vaccines are here. Take the organism, kill it, give to the body. Body will thought enemy is there, and they will generate the immunity as well as they generate the memory B cells, memory T cells. So in future you are protected. Okay. And good example is Covaxin. Against the coronavirus, Covaxin is the example. Till today, we use the traditional vaccines. There is a next challenge is rather than taking the whole organism, whole virus or organism, you use only one protein of it. One protein of it, which we call antigen. So Covaxin, Moderna, number of vaccines, they are based on the one protein called spike protein, which is the surface protein of the coronavirus. There is a surface protein, which is called spike protein of the coronavirus, which is used as a vaccine. Rather than using the whole content of the virus, they use only the one protein which is outside it. Okay. So that's an example. But what we are working, or other people are working, that instead of that using the whole protein, can we use the segment only? Segment of the protein, which can serve as a vaccine candidate. So over the year, what we are doing, trying to minimize the size of vaccine candidate. The idea is how to reduce the toxicity or other side effects. So that's a challenge. And in this business, we have to understand the whole area. I'm not covering here. We have to understand how the immune system works. So I'm jumping that part. This is a new thing we started. Because I was discussing today with my with Sudipto that whenever we want to work, we have not to work in the same area where everybody is working. Because the problem is here, if you work in the same area, then you are just thinking, you are doing optimization or over optimization. So we are in the biological field, we have to think about the new problems rather than making the problem perfect. So our aim is always to go one step ahead. So here we propose vaccine adjuvants. Whenever you give the drugs or vaccine to anybody, whether drug work or not work, vaccine work or not work, there is a one word called adjuvants, SBO, and that sort of thing. It is given with the drug and it works. It activates your immune system. That's the most important part. No vaccine will work, nothing will work till the signal will go to the body that some enemy is there. And that's basically innate immune system. So we develop the tools which can predict vaccine adjuvants, that may be peptide based, maybe RNA based, or DNA based. We are going towards the more biological molecule based vaccine adjuvants. So these are the tools sometimes as a researcher, this is a responsibility. This is responsibility that you have to provide your services to the community. Let's say coronavirus was there, earlier Zika virus was there, the earlier Ebola virus was there. Question is how we can contribute, because we don't have any experimental lab. I cannot do any experiment, but at least I can do the theoretical predictions based on the existing tools or based on my tools, and can say these are the possible vaccine candidates, these are the possible drug targets, these are the possible drug molecules. So what we did, we create a resource here. We provide the complete comprehensive information, whatever possible, about the coronavirus. So sometimes my students have the question, sir, what we will get? Because anybody can use it. These are all resources are free. All resources are free, and anybody can take it. They may sometimes give the credit to us, acknowledge us, sometimes doesn't. I say, don't worry about it. Just think you are contributing to society something, so you will get the satisfaction. So we do this type of work regularly whenever is required, because that's our responsibility. And recently we collect and compile all the bacterial vaccines, because bacterial vaccines are there, vaccines which are already designed for bacteria. So if we want to work, we should have the complete comprehensive information at a single platform. There was no database, so we created this recent database for this purpose. Similarly, we create for the viral vaccines. Okay, the idea is that we are creating the database. This is a laborious work, this labor-oriented work. We have to read the whole literature. From the literature, we have to extract the information. We have to put. That's called manually curated databases. All are experimentally verified data. Later on, maybe not. People will take the data set from this or generate the data set from this database, and they will do the development. So development of database is very important. So this is some of the tools related to the vaccine development. There is another area called disease biomarkers, means where you have to identify the disease, or you want to know the status of the disease, or you want to know the outcome, what is the risk of the disease. So these are the different type of biomarkers. Okay. So this is an example of disease biomarkers. And nowadays, there is another area, mobile apps or healthcare telemedicine are there. So these are some of the examples. So this is just a simple presentation, whatever. Why today? What I want to discuss with you is the challenge in today's time. Because I will tell you, the paper we published 20 years back is much easier than to publish the paper today. Why? Because there is too much advancement, continuous advancement, and reviewer asks everything. Reviewer or editor asks everything. You put here. Okay, so you have to be ready. New generation have a more pressure, more work than the old generation. The papers I can publish, let's say 20 years back, it's for very much easier than in today's time. I cannot publish today that same paper.
But actually, that time source was limited.
Yes, you may be
Limited.
But if I publish the same paper, I cannot publish it.
No, that is.
So I mean to say there is too much advancement in the area.
Resource also available.
Yeah. Okay. So here I have few words. Let's say I talk to number of computer science persons. They simply say they want to contribute to the biomedicine or biomedical. That's not a problem. But we don't know the what is biology, okay, or biomedical applications. So I simply say, if you are talking about machine learning, deep learning, mainly. So mainly machine learning or deep learning mainly is heavily used for classification of objects or regression type of problems, real life value prediction. Okay. So here, in biomedical application, it's not different. Why? Let's say this protein or peptide, most of the biological molecules, they go to the around the protein and peptides. Or maybe let's say DNA sequence or RNA sequence. They are nothing, it's like a text stick. Because your text, literature, is made of 26 characters of English. Okay? Here, protein is made of 20 amino acids. Nucleotide sequence is made of 4 nucleotides only. You have to just generate the features. After generating the feature, it's the same problem. So you can apply the same, if you are expert in the field of text classification, you can easily apply the same thing in the protein classification. It's not different. So you should not worry too much about it. This is the one problem. Second problem is nowadays is a gene expression or transcriptomics. Transcriptomics is nothing. It's a, let's say 20,000 genes. For each sample, we have the different gene expressions. So you have the matrix. Let's say you have the 200 samples. So 20,000 genes are there. So there is a matrix 200 by 20,000. For a computer science, if you get the matrix, then applying the machine learning or deep learning is not a challenge at all. Actually. So I will encourage you to jump in this type of area. It's not so difficult actually. Just consider it's an object. Same, we go to the chemoinformatics. In chemoinformatics, what we use? Small chemicals. Consider small chemical as a object. You can generate the different features or descriptors by just calculating what is charge, volume, size. The different descriptors are there. Once you have the descriptor of the chemical, you can use it. So it's not complex problem. Image classification, of course, you are using your field, computer science. Same, we have the biological problems. We have the person, disease person, or healthy person, or the cancer, different stage. You can do the same type of classification there as well. So I mean to say, if you are computer professional, it's not so difficult. I will put the other statement as well. If you are biologist and you want to apply the computer science, don't worry too much. There are too many libraries are there to implement the machine learning, deep learning, all these techniques. It's not as complex as earlier. Because if you go to the Python library, too many Python libraries are there. This scikit is there, this Keras is there, PyTorch is there. Just learn it in a few days and implement it. I mean to say, problem is not so difficult. Now, I want to discuss now the case where what type of challenge we are facing and how we have to solve it. Recently, we developed a improved version of our software called ToxinPred. ToxinPred is a well-known software in the public which is used for predicting toxicity of peptides. It is heavily used worldwide. Okay, 300 citations per year. Okay, but it has been developed 10 years back, and meantime, data has been more than 5 times actually. New data has come. So we thought that we will develop the updated version. We developed the updated version. Earlier, we used simple machine learning technique and we published it. No problem. This time, we were put too many comments and still it is not published. And what type of techniques we have used it recently and how we solve this problem. I am giving the example. So first we have to understand what is the problem. Problem is very simple. You have the peptide. You may consider it's a text string or words. You may consider it's a words. Let's say in the text, you have the words. These are the words which have the property called toxicity. These are the words which does not have the toxicity. Question is, if anybody give you the new word, can you tell me that whether it's a toxic or non-toxic? Very simple binary classification, nothing more than that. Okay. So first thing, we normally do the compositional analysis. Because all peptides, they are made of 20 type of amino acids. Okay. you can calculate their composition. So by composition, you can simply identify whether the composition for toxic and non-toxic, how it is different. We also compare with the older one, toxin PrEP positive. So there are two positive, one negative. So it will tell you, because sometimes before you apply it in machine learning, deep learning or anything, you have to perform simple analysis. That's called common sense. I simply say machine learning, deep learning, all these things, they are nothing more than that common sense. You use your common sense. If there is a compositional biasness between the toxic and non-toxic peptide, you can easily classify damage. If there is no compositional biasness, then you have to use some other techniques. So here, even the composition biasness is there, it is visible. Then we do the next analysis, position-wise biasness. Positional biasness, whether a particular residue is preferred at the particular position in the peptide. This type of analysis is important to understand from biological point of view which position, which residue is preferred, or in toxic peptide, which residue is preferred. One thing is very clear, most of the toxic peptide, cysteine is heavily dominated. Why? Because cysteine provides the stability to the peptide. If it is stable, it stays long in your body, then it will be toxic. So these are the simple things you have to do the initially simple analysis. So this is the example that how we sort of first we create data set from different servers. These are the different servers where experimentally validated data is there. Please remember, we have to use the experimentally validated data. Data set is most important part actually of any prediction method, because junk data set will give the junk prediction. Once you have the data set, so here we have the 5,540 toxic peptide, equal number of non-toxic peptide we have selected, and then we have created the dividing into the training and validation side. That's another thing I was discussing with somebody, that most of the time we take the data and then we run the machine learning. Please remember, it will not work. You have to have one independent data set which is not used for any training testing. You have to have some data. So we create the 20% data separately, keep not used in any learning. Then we use the 80% data for training and testing or parameter optimization by using the 5-fold cross validation. I'm not saying use 5-fold cross validation only. You may use a 7-fold cross validation, leave one out cross validation. It's your choice, depending on size and other. Use that part. Then we use the two techniques. One is called alignment free prediction and alignment based prediction. Please remember, in biological sciences, biologists will hardly go to the machine learning. Before machine learning, we already have the powerful tools to annotate the function of a protein or peptide. What are these tools? One is similarity based search. BLAST is, everybody know, who is a biologist, they know what is a BLAST. BLAST is a software used for performing the similarity search. Because in biological sciences, if two sequences are highly similar, then the chances is there high that they will have the similar functions. That work very well. So if high similarity is there, then you can use the BLAST. So we use the BLAST to see whether BLAST will work or not. In our case, BLAST have the high specificity, means whenever high similarity is there, then it works well, but poor coverage, not able to predict many sequences because no similar sequence are there. There is another thing, motif, or we call pattern recognition. Pattern recognition or motif. These are the small molecules, small regions of the sequence, not the whole sequence. Two sequences are not necessarily they are similar to each other, but maybe there is a small region which is responsible for a particular function. So we have to do the motif search. So alignment based, we have used the similarity based or motive type of search. All right. Then now it's a question of feature engineering. First goal is, when you want to apply the machine learning or deep learning, we normally have to focus on the feature extraction, because that's the most important part for us. So we use our own software called P-feature. But recently we got the comment from the reviewer, why you are not using the language models, protein language models, to get the embeddings which is generated by the language model and use them as a feature. So we use that as a feature also. The next was the feature selection method. So we use nearly all the feature selection methods, whatever the best we can do. Then machine learning models, we try all these extra trees, RF, SPM, whatever is possible. DL models, of course, we use CNN, LSTM, whatever. This time, earlier we never used in our group. This time they force us to use the large language models for classification. There is two usage of the large language models. One is use their embeddings and use some machine learning for classification. Another is large language model can be used for the classification. Okay, so we use for that classification, and then we combine with the alignment, the similarity based or motive based approach, because that's the power of the biologist and this is the power of the computer scientist. So we combined it, we got it. Please remember one thing. That's a problem in the literature we are facing from last number. We are fighting with the people actually. There is some problem. People feel that more advanced technology, more advanced technique will be highly accurate. It is not necessary. I am giving again a statement. It is domain specific. In our case, simple amino acid composition and dipeptide composition based features, that's a 420, using the extra tree models, machine learning, give the best result, better than any large language models or their embeddings or all these things. Even the large feature selection doesn't work, the simple work. This is the problem, because when you talk in the same tune where the world is talking, then it's easy to publish, but you are going in the wrong direction. So you have to check everything, even simple thing work, then say it's a simple thing work. If anybody want to prove the wrong, let's try it. And it is not the first case. Number of times we have demonstrated our case. But I'm not saying that advanced models are not good. They are maybe good in their own domains. So I mean to say, if you want to work, you have to systematically try all these technology. Then you say that this is the best technology for this domain, and then you do it. So this is a just example. Yeah. So I'm not going into the results because I have already described the part. So now there is another thing for the youngsters. You have to, so by explainable AI actually, because this time reviewer asked us that whenever you are doing the prediction, you have to give the explanation of the features, which feature is responsible for the prediction of toxicity or non-toxicity, whatever is there actually. So if you are the young, I will say these are the just example of libraries, like particularly SAP library, Lime library, they are very good libraries, which you can easily use. And now it's a post hoc conditions, you can apply them actually. There are a number of libraries, are they like Scikit? There are a number of libraries for deep learning or language models. So you can use it. I mean to say, do not scare with all these big words. You can do it easily. Just try it. Nowadays, life has become very simple in that term that you can easily implement the technique. Earlier, in simple techniques, we have to, but same time you have to learn all these techniques. Anyway, so thank you very much. Here, I'm giving you the example that in Indian system we work, that all papers, we have not worked from abroad or anywhere, we work from India itself actually. All these things will be heavily cited if you maintain your softwares and databases in the long term. That's a message actually. That sometimes what happens, we say publish and forget about it. That's not the right attitude, particularly in the field of computer science where you are developing some software or you have to maintain in the long term. So somebody can use it. Actually. So that's all. Thank you very much.
Yeah, any question?
Yes. How did you select the non-toxic peptides?
Yes. Some non-toxic peptide we already get from the literature. Because that's a very interesting question you have asked. Why this is an interesting question? Because a long time back, let's say 20 years back, we tried to establish the non-toxic or we developed a database called MSC binders. So there are a number of databases. So in that database, we put first time MSC non-binders. So they say biologists never reported MSC non-binders. From where you will get the MSC non-binders? I say, look, they check. We go to the research. We check in this protein. This is a region which is top, let's say MSC binder. So rest of the region which they check it, they have not reported anything. It means that is a non-binder.
No, but I'm asking because so maybe today it is non-toxic, so thereby it is toxicity in some other angle, some other aspect. So is it guaranteed? So for toxic peptide, it is guaranteed that it is toxic for something, but for non-toxicity, it is not guaranteed. I'm trying to say that.
No, yes, I agree with you, but there are most of the people when they do the experiments, they take the peptides, they put in the same condition. In same condition, some peptides are toxic, some are non-toxic. So the chances is there that they are non-toxic. Still, I agree with you. That's no guarantee. That's a whole part in the biological sciences. Still, we are not able to solve many things because there are too many variables are there. Let's say, for example, you have no allergy till today. After a certain age, you become the allergy. Now, how you can say that same food you become allergic? How you will explain it? Because your system is changing.
And have you got the balance data? Means I think data imbalance will be there in toxic versus non-toxic.
Here we have taken the balance data, we have cut the data. But we can go for the real data.
Oh, thank you.
Any other question? I will just ask maybe not very intelligent question. All these analysis pattern recognition is based on text. Now, how far have you progressed in recognizing image classification? I mean, how do you classify image? The same technique or is it different?
I think nowadays, whatever I know, the CNN work very well. Convolutional neural network work much better than the most of the previous techniques. Because in the convolutional neural network, they are not taking only global, but they are recognizing local objects. Let's say if I see from long distance, then I recognize that wheel is there, then it belongs to the car or that sort of thing. So CNN works very good.
Okay, I think let's thank Professor Raghava again for a wonderful talk. Has something to say on
Yes, yes, yes.
Hello. Thank you, Professor Raghava, for the wonderful talk, and thank you, Professor Chakraborty, for conducting the session for us. Now, I request Professor Chakraborty to please felicitate Professor Raghava with the medal. and request Professor Rajiv Kumar Dave of Indian Statistical Institute to please come on stage and felicitate Professor Chakraborty with the medal.
It should speed up the lunch. Let's go for lunch. Okay, yeah. Let's go for lunch.
Yeah.
Now we have a lunch break. Please collect your lunch packets at the back of the corridor of the hall. Post lunch, we have